interesting is the data theft problem, but that's in fact the reason we gather that kind of data and the reason we developed the software and we did what we're going to show in the rest of the presentation. Okay. After that first report, we tried to gather some other kind of data. We needed to gather a quantitative measure of how a Bluetooth worm could easily spread. And that measure is also needed to implement mathematical models or to do simulation to see how effective will be a Bluetooth worm. We also needed to gather the average number that a Bluetooth worm could propagate to, being propagated by a single device, so not using something like the blue bag. And of course, as I said earlier, we wanted to know exactly how high could be the success rate of a social engineering propagation technique. And that number is quite high, in fact. We did some tests, and more than the 10% of the devices of people, of the users, actually accept a transfer from unknown people. Okay. There's some sort of intrinsic limit in a tool like the blue bag or any other tool that can be used to do survey. That is, it can be used only to do end-to-end inquiry. That is, M dongles in the blue bag to N devices in contemporary, but no more. To get some more realistic data, we implemented a framework that can be used to do distributed surveying. So we have agents that can be spread by the blue bag or other devices, spread in a good way, so that other devices can distributedly help doing that scan, so we could survey a wider area and so on. And that devices just do the inquiry, save log data, and return the results back to the blue bag. Okay, a little bit of the internals, quite simple. Our agents are composed by an envelope and a payload. The envelope is a piece of software that just scans for Bluetooth devices and tries to propagate itself to that devices. It has a list of targets, that is, a list of users that wish to help doing the survey, and it tries to propagate only to that group of targets. When propagated, it deploys what we call the payload, which is just a piece of software to be executed on the victims. That piece of software collects data, generates logs, and sends these logs back to the blue bag via Bluetooth, or in fact using, could use SMS, could use emails or whatever. Okay, couple simple pictures. On the right, kind of stupid picture, they show us the blue bag that see some devices in its range and tries to propagate that devices, and these devices itself then propagate to other devices, the envelope, the payload, and return results back. The envelope is really nothing more than a huge if. If the code is executed on the target, it executes the run method of the payload to do the task assigned. Otherwise, it just tries to scan for devices and tries to propagate to that devices. Okay, of course, having a target list and a group of payloads enable us to deploy different payloads to different targets to do whatever we want. How can that thing actually propagate? worms up to now propagate using almost exclusively that kind of social engineering techniques. The Kabir A worm, the Lesko A worm, substantially tries to scan for devices and try to push itself to other devices. And if the user accepts, then they install themselves. At present, they don't exploit any kind of vulnerabilities, but there's nothing stopping or that could not make possible to use vulnerabilities to attack devices and deploy some counter software using the right vulnerability. Okay, up to that point, we have a tool that can do that sort of distributed scanning, quite effective, can deploy software agents to devices, can propagate as a worm would do, but can be propagated, for example, by the blue bag, so in a more effective way, because the blue bag has many dongles, so it's quite effective, beside its coveredness. And these agents can carry payloads, can execute themselves on the targets, return results back, and so on. Okay. From now on, the agents could do many other things, in fact, because they're quite, our framework is quite generic. We use it for distributed serving, but we could give agents a specific target so that these envelopes tries to propagate right to a specific target. The payloads could do whatever, also evil things, because when you can execute something on the device, you can do anything. They could keylog, they could sniff, record the audio, or whatever. And what's kind of interesting, they could return results back using emails. They could do HTTP requests to a malicious web server that logs the data. And everything maybe without ever getting into the range of the victim, because the propagation makes possible to make the payload arrive on the device being quite far, and the results can return back not only via Bluetooth. Okay. We clearly couldn't test that in a real situation because it's not kind of fair. Then we tried some sort of academical, probably, way. We studied the mathematical models that are used to model epidemic spreading, but that are used and applied quite successfully also to study the propagation of computer viruses. The most used and effective models are the Kermack and McKendrick models. These models are developed to be applied in homogeneous environment, that is, like the internet, or environment in which the probability to find vulnerable or immune subject individuals is quite homogeneous. And they require that the spreading doesn't suffer from the geographical locality. So if you think about a computer virus spreading, its spreading is not affected by a geographical factor, because in fact, using the internet, it can infect a computer everywhere. That's a completely different environment from the one in which the blue bag would apply, because we are very affected by the geographical factor, because the propagation must be performed by a Bluetooth. So a range that can be at maximum 100 meters, a kind of geographical constraint. Okay, due that this hypothesis doesn't apply, we try to go the simulation path. Okay, we choose a simulation propagation scenario, which we'll show in a couple of slides. We try to choose reasonable parameters for that simulation. And actually, we use the data that we collected during the survey, looking for these stupid people, which in fact are the largest percentage of the device that we can consider vulnerable, because a user that accepts a data transfer is considered vulnerable. Okay. Using that simulation, we wanted to estimate how effective a malware that propagates that way will be really successful. There's a quite tough problem, because it's not easy to describe the movements of a large number of devices in space. It's quite difficult, cannot be done by hand. We found a very interesting work by two Italian researchers that are actually working in the UK. Their latest work is a community-based mobility model for ad hoc network research. Their work applies, in fact, to ad hoc networks, but is perfect also in our case. And they developed a tool that can generate movement traces of devices, of nodes of a network. You can specify the minimum and maximum speed of these nodes and another bunch of parameters. We built actually a simulator, some sort of simple network simulator that uses these traces as input. These traces tells him that the node 11 at x instant of time is displacing to a point in space with a defined speed. And that simulators try to mimic the behavior of a worm spreading. So a piece of software that scans for devices, tries to transfer, wait for an answer from their victims, and so on. We are in fact trying to develop an evolution of that simulator using the NS2 network simulator. The NS2 network simulator will be probably useful to get more physically sound results, because it will take into account also radio collision and that kind of details. Okay. Okay, we consider a simple simulation context. We consider a shopping mall with the surface you can see in the slide, 78 shops and something like that. That's a